Welcome to this video on derivatives. This time we're going to discuss related rates. So what is a related rates problem? We already know that derivatives express the rate of change of a quantity with respect to time. In related rates problems, several quantities are somehow related to one another. When you change one of these quantities, it causes a change in the other. A good example will be a spherical balloon. When you add air to the balloon, both the volume and the radius of the balloon are increasing. The rates of change of the radius and the volume are related by the geometry of the problem. So we know our equation for the volume of a sphere is 4/3 pi r cubed. So you can see if the radius increases, the volume will also increase. So we're going to learn how to calculate these two rates, the change in the radius with respect to time and the change in the volume with respect to time, and to compare those two rates of change. So how do you set up a related rates problem? First, you draw a picture and you define and label variables. There's a lot of geometry involved in this part of calculus. Then we state the given information in terms of our variables. Then we write an equation which relates these variables based on the geometry. We need to be sure not to substitute known quantities too early into our equations, or we may end up differentiating constants and end up with an equation that says something that isn't true. We differentiate both sides of the equation with respect to the independent variable. Usually this will be time, using the chain rule. After this, we now have an equation relating rates. At this point, we substitute our known quantities and we solve for the unknown rate, the rate that we're being asked to find in the problem. So in this example here, we're asked to find dx dt, so that the implication here is that x is a function of time at x is equal to 3 if y is equal to 6x squared minus 8, and given that dy dt is equal to 5. So that means y is also changing with respect to time. The change in y with respect to time is 5. So we're trying to find the change in x with respect to time. So both x and y are changing with time. So we're going to differentiate with respect to time. Time is our independent variable. So my equation is y is equal to 6x squared minus 8. I'm going to differentiate both sides with respect to time. So on the left, the derivative of y with respect to time, that's all we have on the left, is equal to 2 times 6x times, using the chain rule, the derivative of x with respect to time, and then the derivative of negative 8 is simply 0. So we have dy dt is equal to 12x times dx dt. Now, we're looking for dx dt, but we're given x is equal to 3, and we're given dy dt is equal to 5. So I'm going to substitute 5 for dy dt and 3 for x, which leaves me with only one unknown, which is the derivative of x with respect to time. So that's 5 is equal to 36 dx dt. Dividing by 36, then I will have dx dt is equal to 5 over 36. And that's my solution. I found the rate of change of x with respect to time. Sample 2 says a spherical snowball is melting. Its radius is decreasing at a rate of 0.5 centimeters per minute. At what rate is the volume of the snowball decreasing? when the radius is 15 centimeters. So we have a snowball shaped like a sphere, and here's its radius. So the volume of a sphere is 4/3 pi times the radius cubed. And we're told that the radius is decreasing at a rate of 0.5 centimeters per minute. So once again, the independent variable is time. So we're differentiating with respect to time. So that means I could say that dr dt, the change in radius with respect to time, is decreasing. That means it's negative. So 0.5 is the rate of change of the radius with respect to time. So it says we're interested in finding the change in the volume, the rate of change in the volume with respect to time. We want to know that when x is at 15 centimeters, at that instant. So actually radius in this case is r, when r is 15 centimeters. So we differentiate our volume equation, which relates radius and volume with respect to time. So that's dv dt is equal to 4/3 pi times 3r squared times, using the chain rule, dr dt. So I've differentiated both sides of my volume equation. Now I could simplify that a little. dv dt, cross out the 3's, so that would be 4 pi r squared times the change in radius with respect to time. All right, so now I'm going to substitute in the given radius. At that instant, we want to know what the change in volume with respect to time is. So 4 pi times the radius of 15 squared times the change in radius with respect to time, which we're given as negative 0.5. So if I calculate that number, so typing that in, I get the change in volume with respect to time is negative 450 pi centimeters cubed per minute. Example 3 says the altitude of a triangle is increasing at a rate of 2 centimeters per second. So we've got a triangle. The altitude is the same thing as the height. So there's my altitude. So the altitude of the triangle is increasing at a rate of 2 centimeters per second. So it's going upward at 2 centimeters per second. The area is increasing at a rate of 3 centimeters squared per second. So that's the change in area with respect to time is 3 centimeters squared per second. All right, let's write dH dt in my list over here too. dH dt, change in altitude with respect to time, is 2 centimeters per second. We're asked at what rate is the base changing. So here's my base, this side over here. So we want to find out what is dB dt at the instant the altitude, so that's when h is 10 centimeters, and the area is 105 centimeters squared. All right, so we need an equation that pulls all these variables together. So we know the area of a triangle is 1/2 the base times the height. So that pulls all of our variables into one equation. So we can differentiate both sides of this equation with respect to time. So I'm going to differentiate first here, and then I'm going to do my substitutions. Of course, I probably don't need to say that We're differentiating with respect to time because time is my independent variable. So dA dt, change in area with respect to time, is equal to 1/2. So this is a product here. Let's pull the 1/2 outside. So the derivative, the first times the derivative of the second plus the second times the derivative of the first. All right, now we can do our substitutions. So let's just go through our equation and make sure we don't need to calculate anything before we start substituting. So we need the change in the area with respect to time. That's 3. Then base, we don't directly know base, but we know area and h, so we are going to have to calculate base. dH dt is 2. The h is 10, and dB dt is what we're looking for, so this is our unknown right here. So the only thing we need to calculate is the base, and we can do that knowing if area is equal to 1/2 base times the height. At the instant we're interested in, the area is 105, the base we need, and the h is 10. So 105 is equal to 5b, which means b must be 21. All right, so now we have everything. dA dt is 3. B is 21. dH dt is 2. H is 10. And dB dt we need. All right, so let's multiply both sides by 2. And then we can cross out this 2 right here. So that means 6 is equal to 42 plus 10 times dB dt. All right, so 6 minus 42, negative 36, is equal to 10 times dB dt. So dividing by 10, I get dB dt is equal to negative 36 divided by 10. Well, that would be negative 3.6. So this is leading me to believe that the base is shrinking with respect to time. Let's see if that makes sense in our problem. So we said what was happening was that the h was going up. This is growing. So if that's getting bigger, you can imagine that getting pulled up. You can see how that would shrink the base inward. So that makes sense. As you're stretching this triangle upwards, keeping the area the same, of course, the base would have to shrink. That makes sense. All right, so shrinking base. So the change in base with respect to time is negative 3.6. So the units are centimeters. Units of time, we said in this problem were seconds, right? Let's just check seconds, yes. So the change in base with respect to time is negative 3.6 centimeters per second. Okay, so that does it on problem 3. In example 4, it says a 16-foot street light. So I've drawn a diagram. Here's my street light, giving off some light. Shines down on a 6-foot person. So here's the beam of light hitting this person right here and causing this shadow from the person on the ground here. This is my shadow. So this 6-foot person is walking away from the street light, and I've indicated that by this arrow here. So this distance x is the distance between the street light and the person. So the person's speed is the change in this length x with respect to time. So the person is 6 foot. The person is walking away from the street light. at a rate of 3 feet per second. So this dx dt is 3. So given information, dx dt, change in x with respect to time, the person's speed walking away from the street light is 3 feet per second. All right, part A, how fast is the tip of the person's shadow? So here's the tip of the person's shadow moving when she is 20 feet from the pole. So we're interested in the instant in time when this person is 20 feet from the pole. And what they're asking for here in A is how fast is this tip moving? That's dB dt, this tip right here. This length B is changing. How fast is it changing? Right, so we need an equation. So in order to figure out an equation, we take into account similar triangles. So we have this smaller triangle here has the same proportions. It's similar to this larger triangle here. And we know that because they share this same angle, so that's one angle that's congruent between these two triangles. And they also share a right angle. So anytime two triangles have two congruent angles, the third will also be the same, and therefore they'll just be enlargements. They'll be similar of one another. So we can set up proportions. We can say that 16 over this longer side, which we're calling B, 16 over B, would be the same proportions, the same fraction as 6 over this side S. 6 over S. All right, so we can say that S is B minus X, because we don't need S in our equation. We don't want to have that many variables. So S is the same thing as B minus X. All right, so now if I carry through some cross multiplying here, I'll have 6b is equal to 16b minus 16x. Combining like terms, I'll get an equation that says 10b equals 16x. Right, this is my equation. 10b is 16x equation. Now I want to differentiate with respect to time. So that means the derivative of 10b would be 10 using the chain rule times the derivative of b with respect to time. And then on the right, the derivative of 16x is just 16 using the chain rule times dx dt. Right, so now we're going to substitute. So what we're trying to solve for, according to part A, is how fast is the tip of the person's shadow. That's going to be this here. How fast dB dt. So we're looking for dB dt. So this is our unknown. So we need to have dx dt in order to be able to solve for dB dt. All right, so we know dx dt up here is 3 feet per second. So substituting in here, we've got 10 times dB dt is equal to 16 times dx dt, which is 3. So that means dB dt is 48 over 10. Right, so that's equal to 4.8 feet per second. All right, so we've got that now. The next part is B. So B says, how fast is the shadow lengthening when she's 20 feet from the pole? So that means we want the change in the length of the shadow with respect to time. So that would be ds dt. So from just looking at these lengths on the bottom here, we know that x plus s is equal to b, or we could say s is equal to b minus x, and that would relate those three quantities. So let's just start with that. So we're trying to find ds dt, and we said that s is equal to b minus x. Okay, so that's going to be my equation. I think I've run out of space at the bottom here. So we'll go over here. All right, so if I differentiate that equation, I've got ds dt is equal to db dt minus dx dt. All right, so we already know that dB dt is 4.8. And we were given that dx dt is 3. So this is pretty straightforward to find ds dt. Subtracting 3, I'll get 1.8 feet per second. Now the interesting thing about this problem is that none of these quantities were dependent on how far this person was from the pole. Notice how that distance, 20 feet, didn't play into any of these calculations. All right, so that's kind of interesting. It doesn't matter how far this person is from the light source. The rate of change of the length of the shadow and the rate of change of the length of the base there, the tip of that shadow, the movement of the tip of that shadow doesn't depend on how far the person is from the light source. Okay, so we've solved that one. So in example 5, I've drawn a diagram already. It says an inverted, that just means upside down cone, conical tank is being filled with water. So here's my water line. This is my water here. This part down here is my water. At a rate of 15 cubic meters per minute. The diameter of the cone, that's this dimension here, is 8 meters, and the height of the cone here is 11 meters. We're asked to find the rate of change of the height of the water, that's this height here, in the tank when it is 5 meters deep, when h is 5. So our given information is that the change in volume with respect to time, and that's what's meant by being filled with water, that's your volume, the volume of water, is 15 cubic meters per minute. All right, we also know that the diameter of the cone is 8. The height of the cone is 11. This is all in meters. All right, and we're asked to find the rate of change of the height of the water, dH dt, when the water is 5 meters deep. All right. So let's set up our equation for volume. Our equation for the volume of a cone is equal to 1/3 pi r squared h. All right, so let's see what we know. So in my equation, I've got V I've got R, so V, R, and H. Okay, so I'm interested in dH dt. All right, so I don't really need to have an R in my equation, so I really want to get that R in terms of H. So I can do that if I take a side view of my cone here along the midline, and I put, so that would be, this distance here would be 4, half of 8. Here's 4. The height is 11. All right, so I can draw a line right here to represent this line here, which is R. And then also this amount here would be H, and if I draw that on this little smaller diagram, H would be right here. So this is the R in my equation, and this is the H in my equation. Okay, these overall dimensions right here are just going to be constants. Okay, so my variables are here, here, in my drawing over here. R is here, H is here. So I can use the similar triangles idea again. So this side here, 4 over 11, 4 over 11 is proportionate to R over H. 4 over 11 is proportionate to R over H. So that means 11R is equal to 4H, or R is equal to 4/11 times H. Now I can use that knowledge to go over here and in my equation say R is now going to be 4/11 times H. Now square R multiplied by H. So right now I've got my equation in terms of only H and V. So that'll help me out with my differentiating and substituting here. So that's 16 over 121, squaring 4/11, then pi. Then I've got 3 h's multiplied together, that's h cubed. All right, so here's my equation right there. So now I can differentiate with respect to time. So dv dt, so h is my variable, so 3 in the front. Drop it down to 2, and then chain rule dh dt. H is also a function of time. All right, so I can cross out these 3's here. Now I have to do my substitutions. So I'm solving for what I'm asked for here was find the rate of change of the height of the water when it is 5 meters deep. All right, so that means H is 5, and I'm also given that the change in volume with respect to time is 15 meters cubed per minute. So I can use those as my substitutions. So I have 15 for dv dt, and then substituting for H, we said H was 5, so 5 squared is, let's put 25. So the only thing left is dh dt, and this is what we want to solve for. That's what we want to find. So if I want to solve for dh dt, I can just multiply by the reciprocal of this business here. So that's what I've done. And if I run this through the calculator, I'll be able to get that dh dt is equal to 1.444 meters per minute. Okay, and that answers the question. What is the change in the height of the water with respect to time when the height is 5? So we've done it. We've solved our related rate problem. So in this example 6, it says a plane is flying at a constant altitude of 12 kilometers. So that's 12 kilometers here, constant altitude. And he's flying at a speed of 505 kilometers per hour. And I'm going to call that dx dt, where this is my x distance and this is my y distance. Then it says, what is the rate of change of the angle of elevation when the plane is at a horizontal distance? So that would be my x distance of 135 kilometers from the observer. So my observer's down here. So my observer's looking up at the plane right here. So from the horizontal angle of elevation, straight along this line of sight is my angle theta. So we're trying to find what is the rate of change of the angle of elevation when the plane is at a horizontal distance of 135 kilometers from the observer here. All right, so we need to, let's just write down our givens first. Our givens are dx dt, that's the speed of the plane, is 505 kilometers per hour. And that's also signifies the rate of change of the x in my diagram with respect to time. The other thing we know is that x at that instant that we're interested in is 135 kilometers. The y is a constant, 12 kilometers. That's not changing. And let's see, what else do we know? That's all we know. So now we need an equation. So an equation for theta, because we want to differentiate theta with respect to time. So in this diagram right here, this is y on this side, so that would be the opposite side, and then x would be the adjacent side. So our equation can simply be the tangent of theta is equal to y over x, and that brings in a relationship between all of our variables. All right, so that's our equation. Now we can differentiate that equation with respect to time. So the derivative of the tangent of theta is the secant squared of theta, d theta dt. Chain rule. And then on the right-hand side, we've got a quotient. So we've got the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Now we'll go ahead and do our substitutions. So we need the secant squared of theta. We need d theta dt. That's what we're solving for, so we don't know that. This is our unknown. And then we need x dy dt. Here's x again. We need y, and we need dx dt. Okay, so we're going to have to calculate some of this stuff here using our right triangle trigonometry. So if we have this triangle right here, here's theta. At the instant in time that we're interested in, we're told that this side is 135. We know that this side is always 12. The height of the plane, the altitude the plane is flying is not going to change. So I can use Pythagorean theorem and just say 12 squared plus 135 squared. Square root of that is going to give me my hypotenuse. And my hypotenuse comes out to be 135.53224. Now you want to carry out a bunch of digits because we have a small angle with this kind of a very small side here compared to the larger side here. It's going to be a small angle. So carry out a bunch of digits here. We don't want to lose that. So now I can say the secant of theta is equal to the hypotenuse over the adjacent side, 135, 5,32284 over 135. Right, so I really need the secant squared. Let's just go ahead and figure that number out. So if I square that number there, I did that already, and I get this number here, and I'm going to keep a lot of digits. Okay, so now substituting into my equation, let's see what we can do before substituting that secant squared number in there. We know that the dy dt, the change in y with respect to time, well, if y is always constant, then the change in a constant with respect to time is 0. This term is just 0. So we can say d theta dt is equal to negative y dx dt, that's my numerator, divided by secant squared of theta times x squared. Alright, so now we can substitute in there. I'll move it over a little. D theta dt is equal to negative y. Y is always 12. Dx dt was 505. That's here. Speed of the plane. Secant squared is 1 point. X is 135 squared. So d theta dt, after typing all that in, I get negative 0.3299. Now this is the change in the angle with respect to time. Those units are radians per time. We're using hours in this problem. So I've got d theta dt is equal to this decreasing rate of change. Now let's see if that makes sense. So is the angle decreasing? Well, if the plane is flying away from the observer, then this angle will definitely get smaller the further this plane is from the observer. Okay, so a negative rate of change of theta with respect to time makes sense in this problem. So we've solved this related rate problem. So for our last example, we have a 15-foot ladder leaning against a wall. We'll call the wall side Y, and the ground here, side X. So the distance between the base of the ladder and the wall is X. And of course the 15 would be the length of the ladder. It says the base of the ladder starts to slip away from the wall at a rate of 0.2 feet per second. So this point right here is moving this way away from the wall, and we'll call that dx dt. Part A says how fast will the top of the ladder, that's this point here, be sliding downward when the ladder is 5 feet from the wall. All right, so part A says find dy dt when x is equal to 5, and let's see what else, and dx dt is equal to 0.2. All right, so our equation will just be Pythagorean theorem. 15 squared, that's 225, right? So 15 squared. All right, so this is our equation. Now we need to differentiate. So that's 2x times the derivative of x with respect to t plus 2y times derivative of y with respect to t is equal to 0. All right, so we differentiated. All right, now we'll substitute. So we know x is 5, dx dt is 0.2. We don't know y, we have to calculate that, and we're trying to find dy dt. Okay, so over here we know that x squared plus y squared is 225. When x is 5, that means y squared is 225 minus 5 squared. That's 200. So y is equal to the square root of 200. So that goes here when x is 5. All right, so now dy dt is going to be, if we solve that for dy dt, we'll get minus 2 times 5 times 0.2 over 2 times root 200. And that comes out to be, if you type it into your calculator, negative 0.0707 feet per second. So that point dy dt, that point at the top of the ladder, I should say, is going down. Therefore, we've got a negative. So the length of this side is shrinking when the length of this side is growing, is what that's saying. Okay, now let's do part B. Part B says, what will the rate of change of the angle? So the angle the ladder makes with the ground, that's this angle here. What will the rate of change of that angle be at the same instant? So d theta dt is equal to what when x is equal to 5? And we also know that y is equal to the square root of 200. And while we're at it, we also know that dx dt is 0.2 and dy dt is the one above that we just calculated. All right, so we know all that. So now let's find an equation for theta. So that would be tangent. Tangent of theta is y over x. All right, so we're going to differentiate that. That's our equation. We're going to differentiate that. We'll get the secant squared of theta d theta dt is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. All right, so we can say the secant, let's look at the secant. The secant is the hypotenuse over the adjacent. Well, that's 15 over 5, so that's 3. So we've got secant squared is 9. All right, so we can put the secant squared over here. Let me just put it right here. So I'm afraid I'm going to run out of room instead of in the front there. Okay, so now we put all our numbers in here. So we've got 5 for x, negative 0.0707 for dy dt, root 200 for y. Dx dt is 0.2 all over x squared, secant squared, 3 squared. All right, so I type all that into the calculator, and I get that dy d theta dt is equal to negative 0.014142. And of course, this would be radians per second. Okay, so this concludes the examples that we're going to do for this section on related rates. And what you're going to find as you're working your homework problems is that there is not an example for each one of them, but the principles will be the same about how the series of steps you need to come up with the picture, the drawing, the equation, then differentiate the equation and perform your substitutions. All right, and all of these problems might have a little bit of a different element to them, but the procedure will be basically the same.